So what I'd like to do now is very quickly use this to talk about some other, well, first of all, talk about one property of P. The first property of P that we need to address is the question of, well, is P symmetric? Okay, like is sigma symmetric? We know the Cauchy stress is symmetric. The question is P symmetric? Okay, if you look at the relation for P up here, and you think of taking its transpose, it should be pretty clear that it's not symmetric. Okay, and so let's just do that. So note, if you look at P transpose, well, let me first write P and then I'll write P transpose. P is J sigma F inverse transpose. What this implies is that P transpose equals J F inverse sigma transpose. Okay, which is J, which is a scalar, F inverse. Now sigma transpose is sigma. Okay. However, in general, we know that this in general is not equal to sigma F inverse transpose. Okay, so P is not symmetric. Okay, in fact, because of the fact that P has one leg, in fact, since coordinate notation reminds us that we have P I J, right? What would the transpose of P be? This thing implies that the coordinate notation of P transpose would be P transpose capital J capital I, right? Now, given the fact that I and J indices don't even live in the same configuration, it's almost vacuous to even ask if P is symmetric, right? Because it's actually meaningless. Maybe in a particular case, if you look at a particular matrix, right, matrix representation of P, you may find that it is symmetric, right? You may find that the matrix representation turns out to be symmetric. But because the two legs of P are in completely different configurations, even if the matrix turns out to be symmetric, it has no fundamental physical interpretation. Okay, it's just a coincidence of the numbers you picked. Unlike the case of sigma, right, where sigma being symmetric is fundamentally meaningful in a physical sense. It says that we have balance of angular momentum. There's no such implication here. Okay? Okay. So what I want to say here is I and J indices are in different configurations so even if the matrix P equals whatever, right? You fill up the matrix P, right? Even if the matrix P is symmetric, right, there is no physical significance of this fact. All right? Okay. All right, but then let's see what we can do with it. But again, we have P equals J sigma F inverse transpose, right? So what this implies, of course, is that if we compute now P F transpose, okay, which is equal to J sigma, this quantity is symmetric, right? Clearly, because sigma is symmetric, right, and J is just a scalar. recognizing this, and because, as we will see, this quantity often shows up when we have integral forms of our relations, this quantity is denoted as tau or tau properly, and it's called the Kirchhoff stress. Okay, clearly tau equals tau transpose. Okay, all right. So what we've done now already is define a third stress tensor, right? As a final step, we ask ourselves, well, can we, however, define a stress that is indeed symmetric and maybe lives on the reference configuration? Okay, because sigma we know is a stress that's fully symmetric, lives in the current configuration. So is tau. Okay, so tau should probably be written as tau ij ei tensor ej. Okay, like sigma, tau has indices in the current configuration. Okay, so can we define a stress in omega naught that is symmetric? Okay, right, and this sort of hankering for a stress that lives in omega naught and is symmetric is because tau also is in omega t. Okay, so can we do something for omega naught? Okay, indeed we can, right? So if we consider P equals J sigma F inverse transpose, we observe that if we were to multiply this on the left by F inverse, and likewise here also put in an F inverse, okay, now we have something on the left hand side that is indeed, sorry, on the right hand side, and therefore on the left hand side, that is symmetric. Okay, and the symmetry becomes clear if we consider what we have on the right hand side here. Okay, because note that J F inverse sigma F inverse transpose, the whole transpose is, what is the transpose of a product of tensors? It is a product of the transposes, but with their orders reversed. Okay, so J just comes along for the right, it's a scalar. So, okay, so if you write all of these in the reversed order but with their transposes, you get back F inverse transpose transpose, but that's F inverse. You get sigma transpose, but that is sigma. Okay, right, and here you get F inverse transpose, right, and you compare the two and you see that, well, it is symmetric. Okay, what this implies then is F inverse P equals F inverse P the whole transpose, which is actually P transpose F inverse transpose. Okay, this is symmetric. And what we do is define capital S equals F inverse P to be the second Piola-Kirchhoff stress tensor. right? That's what we call it, all right? Let's look at how indices work out, right? So coordinate notation. S, and I'm not going to put any indices on it just yet. I have F inverse. We know that the indices of F inverse are of the form capital I, little I. We know that P has indices little I, capital J. The little I gets contracted away, and we are left with indices capital I, capital J. Okay? So this quantity properly has both its indices on the reference configuration. Okay? Right? And it indeed can be thought of as a force per unit reference area where the force itself is directed in some direction along the reference configuration. Okay? Something to note about, so let me just put that down. S force directed in omega naught per unit area in omega naught. Okay? One thing to note though about our second Piola-Kirchhoff stress S is that while it's nice and symmetric and all of that, it is not physically measurable. Okay? The reason is when a body deforms, if you have the real force, that force is always in the current configuration, right? It's always a spatial quantity, right? The body deforms. The arrows is the force. Whether it's in the current configuration or in the reference configuration, the arrow is, when you measure the arrow, measure a vector in space, that is a spatial vector, okay? What the second Piola-Kirchhoff stress does is to somehow use the deformation gradient to say that, all right, you have this in the current configuration, you pull back to the reference configuration, but in doing so, you also remap this vector using F. Okay, so it's as if you're using F to remap the vector to do this. Okay, that is not, it's not physically attainable, right, because you're mathematically taking the vector and remapping it. Okay, so even in an experiment, if you started out with this in the reference configuration, the thing deformed and did this, but the force is oriented similarly, all right, if you were to take the deformation gradient at this point and sort of remap the force, then if you went back to the reference configuration, you may see that the force is oriented differently. That is not something you can access physically. You can only access mathematically using the deformation gradient. Okay? And this is unlike what happens with the first Piola-Kirchhoff stress, where the force is indeed the actual force, which has whatever direction it has in the reference configuration and the current configuration. Likewise, in the current configuration, when you measure the Cauchy stress, right? When you define the Cauchy stress, okay? The force and the area are well defined. The area may be difficult to access, but it's well defined, okay? Right? Even physically, it's well defined physically. You don't need to go to any mathematical construct to talk about the area or the force when you talk about the Cauchy stress. Okay? Not the same with our newly introduced stress. So let me say that it is not physically measurable. Okay? What we always need is the mathematical mapping S equals F inverse P. Okay? And to really see how this works out, observe that now if you take the right hand side and just multiply P with the area vector, right? What you see is that what you're doing here is essentially applying F inverse to that force that we had there. Okay, so you really are taking the force TdA, and sorry, those went a little askew. You're really taking the force TdA and pulling it back using the deformation gradient, right, which is a purely mathematical operation that we're doing. That is what lets us talk about the traction corresponding to S. And it's for this reason that we say it is not physically measurable. You need to go to the mathematics to do it. But it's very useful in computations. Okay, that's why we introduce it. Okay, so we've seen force stress tensors here, and this is a good place to stop with this segment.